queues. In this video, I'm going to be going through what a data structure is, arrays, a reminder of arrays, reminder of what an abstract data type and structure is, the basics of a queue, why we learn about queues, differences between stacks and queues, a past paper question, and building our own queue in C#, and possibly involving some extra techniques like inheritance and other advanced OOP techniques, object-oriented programming techniques. So a reminder what a data structure is. Well, it's where any container of information is going to be our data structure. Why do we have more than one type of data structure? Well, different data structures exist. Some are better than others for different types of data. They're better suited for different types of application. And it's the programmer, you, who must decide which data structures available are the best to use for which case. A very easy example of a data structure that we've already used is an array. An array indexed set of related elements which is finite, so there's a maximum size to this. The index it's indexed and only contains data of one particular data type. And there we have an example of a one-dimensional array visualized. An array of strings where 0 holds the string George, 1 holds the string Sue, and 2 holds the string Mo. And arrays can be many dimensions, and this is a 2-dimensional one. And it could be, for example, a maze. So we're going to move on and remind ourselves what an abstract data type is. Abstract data structure. So the abstract data structures don't exist. Okay, they make use of existing data structures such as arrays for storing data, but they don't actually exist themselves. The idea of something being abstract exists in thought or an idea, but doesn't have a physical or concrete existence or presence. In computer science, an abstract data type, mathematical model for data types where the data type is defined by its behavior from the point of view of a user. What the heck does that mean? Well, this video is going to help you construct your own queue. A queue is an abstract data type. Inside the computer, we don't actually have any data queuing, but we have the data behave like it's queuing. So we have something come into our storage area, have some more things come in, and because it's a queue, the first thing that came into it would be the first thing out of it. And that's where we move on to queue basics. We've got the FIFO. First in, first out. The first thing entering the queue is the first thing out of the queue. Examples of real life queues that you'll have seen or maybe been part of. You've got a linear queue. A linear queue, you're queuing for something and it goes in that FIFO order and there's no exceptions to that. You've got a start point and an end point, and it just, it's queuing for a cinema ticket on a particularly busy release, like you see in that example, or queuing for, in this image, I don't know what they're queuing for, let's say the toilet. The first one in the queue is the first one out of the queue. Circular queues, they're a bit harder to explain in real life, and they'll be easier to explain when we get on to actually how we're going to start implementing this. Priority queues, though. Priority queues, like Fast Track at Alton Towers or similar theme parks. Priority queues are essentially first in, first out, but they've also got a priority attached to them. More important than getting on a ride first, things like A&E departments. So in an accident emergency department, they get you in there and they quickly try and do something called triage. And triage is establishing what priority you've got. So people that have breathing difficulties, well, they're going to get seen before people that are breathing fine. People that are bleeding are going to get seen before people with broken bones. I'm talking about a serious bleed there, not just a paper cut. And people with broken bones are going to get seen before someone with just a cough or a cold. And you'd anticipate that sort of system, that queuing system. But if two people come in at the same time, or one person slightly before another, you'd anticipate the first one, with the same conditions that is, with the same priority, the first one to arrive at the hospital will be dealt with before the first one to leave the hospital. So commands for the queuing system, we've got on queue and dequeue. You can see down here in the bottom right, we dequeue from the front, removing from the queue, and we on queue to the back. If you're joining a queue, you join it at the back, unless you have some sort of priority. And we can use peak, very similar to how it works in a stack. Peak would allow you to see what's at the front of the queue in this case, but not actually remove it from the queue. You're just taking a look, but not taking it off the queue. And errors in queues, well, you're going to have overflow if your queue becomes too large to store, or underflow when you try and remove something from an empty queue. Just skip ahead a minute. Okay, so two common abstract data types, stacks and queues. They've got some differences to them. First one is the description, how they operate. Well, a stack is LIFO, the last one in, first one out, and the queue is FIFO, the first one in, first one out. And yes, you can occasionally get people that will give the opposite. So the opposite of LIFO, last in, first out, would be first in, last out. It's rarely used, but you might get some people suggesting it, so I've put it in there as well. Last in, first out. The queue, first in, first out, or as some people might refer to it, the last in, last out. But they're rarely used. The FIFO and the LIFO are the ones that we go for. The stack has one pointer to the top of the stack. The queue has 2 pointers, one to the front and one to the rear. The front to know where we're going to remove it from, and the rear to know where we're going to add the next thing to the queue. And the queue's got a few more varieties, as we briefly described a moment ago. We've got some linear. The queue just works on a first in, first out basis, no issues at all. Circular we're going to get to in a moment, and priority where it's first in, first out. However, some elements in our queue have a higher priority than others, and they're going to kind of push in. Okay, so we mentioned that the queue was first in, first out, and it had it had 2 pointers, front and rear. So front and rear. Okay. In the initial situation, where the front and rear are pointing to the same position, the queue is empty. It's got nothing in it. There's nothing in this queue. The front and rear pointers to the same location. There's nothing in it. When we want to add to a queue, we will add to where the rear pointer is. So let's add a character. Let's go for A. Add the character A. So it adds it to where the rear pointer currently is, then increments the rear pointer. And the front pointer would stay the same. Front pointer would stay in the same location. So our rear pointer's pointing to the next available space in the queue, the back of the queue. The back of the queue is behind the first element. So we add a few more elements. The front of the queue remains. Let's add B, C, D, and the rear would now be here. If we're wanting to take off from the queue, well, we take off from the front because this is a first in, first out data structure. We'd take off from the front, so we'd get a copy of A, and then the front pointer would move to B. Officially, A would still exist in memory, but it's no longer getting pointed to, so we're not going to be able to remove it again. The front of our queue at this level is going to be B. There's no more elements in front of it according when we've got the pointer to the front there. Okay, we can quite clearly see here that we've got 3 elements in our queue, and we can work that out via the pointers as well. We can work out how many elements in our queue by using the front and rear pointers. If this in fact was an array, the first one would be position 0, 1, 2, 3, 4, 5, 6, 7. So it's an array of size 8 with array positions 0 to 7. In this instance, the front pointer would be at 1 and the rear pointer would be at 4. If we do the rear pointer minus the front pointer, then we will get how many items are in there. In this case, 4 minus 1, 3. So we're able to work out, just using the pointers, how many items we've got in there. Our array is still of size 8, but in terms of our queue, we've got 3 elements there. So we'll dequeue again. So we'll take off the B, the front pointer then increments. Front pointer increments up, and we'll add a few more data items: E, F, and G. And our rear pointer will point to the next empty space. So the next line, I want to add one more data item. So the front pointer remains the same. D, E, and F are in our queue, and G. And if we add H, then our R would become 8 if we're just incrementing it up. At that stage of this linear queue, because the pointer for the rear is the same as the size of the array, Well, it's going to be full, this linear queue. Implementing it in this way with just using an array, it's going to be full. The rear pointer can't move any further up because we can't put any new objects in at position 8 because 8 doesn't exist inside of this array. The array's positions go from 0 to 7, and as we reminded ourselves earlier on in this video, arrays are of a finite size. In this case, my array is 8 in length, therefore it can't go any higher. So we're going to come across a problem when we implement in this way, that we could get to the point where our front pointer and rear pointer are at position 8, we know that if the front pointer equals the rear pointer, that we know that that is when it's an empty an empty queue. And the problem there, well, it's empty, but we can't add to it. Implementing this linear queue in the way where we've got an array which is known as a static data type. Static data type. Being static, it doesn't change in size once the program is running, or once it's been declared. It doesn't change in size. So we can't change it from 8. We would be able to remake this linear queue with a dynamic data structure, and that's a data structure that grows and shrinks, and an example of that would be a list. But we're not going to get into that in this video. We do have a way of making this better, of correcting this, and that would be to use a circular queue. So we've still got our array of size 8. So we've got an array of size 8, and this time we'll just put some values in. So our front pointer just happens to be here, front pointer, and we'll put our rear pointer over here, and we'll just put some values in A, B, C, and D. Last time we saw that every time we incremented the rear pointer, we shouldn't have anything in there, I'm sorry. Let's try and remove it. We saw that when our rear pointer would increment when we got to the last data item, we'll be pointing to position 8, and position 8 doesn't exist in here. Now a circular queue gets round that by when the rear pointer gets to the end, it wraps it around and gets it to point to the front. Not to the front, because hopefully the front is somewhere else, but to the front of the array, to array position 0. So it wraps around, and the same happens if the front pointer would get to there. It'd wrap around and go back to the start in what can be visualized as a circle. So going from this first position of the array, where we've got an empty space here, we're wanting to add a new data item. In this case, we would add it, then increment the rear pointer, but instead of the rear pointer being here, it would wrap around to the front and the rear pointer would point there. Front pointer still pointing here. And then we can keep on adding items because we can add it to wherever the rear pointer is. So E can then go there, F, and then our rear pointer would now be here. Because we haven't removed anything, our front pointer still remains in one place, and all of those remain in place as well. Another way to avoid the problem that we saw in the last slide of the linear queue always running out of memory could be to shift all of the positions down one every single time we remove from the front. Now that's okay, but it's not very efficient because that's having to move 8 positions every single time we remove from the queue. Now that doesn't sound too bad, 8, but if our queue contained a few thousand or a few 100,000 items, all of a sudden every time you're removing one thing from a queue, you're having to move a few 100,000 items, and it's actually got a efficiency or a way of measuring the efficiency of the algorithm of big O n, because as the number of items grows, so does the time it takes to process them. Now, with our circular queue implementation, if we remove from the queue, so we take A off the queue and then we just move the front pointer up by 1, we've not had to move all of the existing data items up. All we've had to do is copy what the front pointer was pointing to and move the front pointer up by 1. So regardless of how many data items I've got, whether I've got 8 or whether I've got 100,000, it will take the same amount of time. So the big O for that one would be constant. And when you've got these things taking milliseconds, and then you times in those milliseconds by hundreds of thousands, it starts to take seconds, minutes, and it starts to increase dramatically. With the circular queue, we do have some other bad issues to work out, such as when the queue is full now. Empty remains the same. When the 2 pointers are in the same position, the queue is going to be empty. But when is the queue going to be full? Let's have a little think about that. So we'll copy out what's currently going on, B, C, E, F, G, and we'll add a few more data items, G, H, and our rear pointer would be here, our rear pointer. The front pointer, because we didn't remove anything, would still be here. Ignore that one for a second. So our next available empty space is here, and you should be thinking, that's fine. We've got an empty space, we can add to the queue. So if we were able to add to the queue, what would happen? Well, we'd put some data item in there, and then we'd move the pointer up by 1. In that situation, the rear and the front pointer would be in the same place, and we know when the front and the rear are in the same place, the queue's empty. So that can't be allowed to happen. So we've got to check for where the rear is not 1 less than the front, or in the second special circumstance where the rear is here and the front is here, checking that the front is not 0 and the rear is not 1 less than the total size of the array. Because in those two situations it's full. So where the rear pointer is 1 less than the front pointer, or the rear pointer is at the last position in the array and the front pointer is at the start position of the array. In those two situations, the queue would be deemed as being full. And it will continue to wrap around. So we'll copy out what we've got so far. E, F, G, H, our empty space for our rear pointer. And then if we took off 2 items, our front pointer would now be over here. So we took off the B and the C, and now pointing to D in our last area here. And then we wanted to take off again. We'd have to make sure that the front pointer wraps around, and the front pointer would be pointing at E now, and the rear pointer remains where it is. So the circular queue, it does wrap around. It wraps the pointers around and makes efficient use of memory. In the example we saw before with the linear queue, it's not making efficient use of memory, as when the front pointer kept moving up, these positions could no longer be pointed to. We just talked about the way of solving it would be to keep the front pointer at the front at position 0 and just move every element down. But as the number of elements grows, it becomes increasingly less efficient, or dramatically less efficient, to do that than to use something like a circular queue, which makes efficient use of that memory and just moves things along. The last type of queue that we were going to talk about was the priority queue. And again, it's still going to have 2 pointers, a pointer to the front and a pointer to the next available space, the rear. But in this case, instead of just storing the data, you've got to store the data and the priority. So in this case, A is my data, and I've chosen red to be of high priority, orangey yellow there to be of medium, and green to be of low priority. So essentially it still works as a queue. You still have the first things in and the first things out. However, if we were to introduce some more high priority things, they would have to come before the medium priority. If we introduce some more medium priority, they would have to come before the low priority, but after the existing mediums. So in this example, we've introduced V of high priority. So when it's had to come into this queue, it's had to go and search through, based on its priority, where it should put it in. The priorities are the same, or they are the highest, so it won't go in front of the A, the C, or the D, because those particular priorities are the same, and the A and C and D were put into the queue first. But when we get to something with a medium priority, we can push the rest of the data items backwards and insert our new one there, because that's where it's going to be in the queue. We've got our high priority ones that have to be done first, so our front pointer there. Our rear pointer would move back one as well, because we've introduced a new data item in here. Although it's not gone in where our rear pointer was pointing to, like in the circular queue or the linear queue, because we've entered a new data and pushed the rest back, the rest have moved by 1 place, so the rear would have to move by 1 place as well. So why do we bother learning about queues? Well, they're heavily used in computer systems. We've got examples of the keyboard buffer. You may have come across a time when you've been typing and typing away, and for some reason, possibly some interrupts, a piece of software or another piece of hardware is taking up the CPU's time, and it doesn't type out as fast as you're typing. What it does is keeps all of your key presses in a queue, in what they're calling a buffer, and when it does come back to listening, say it was Microsoft Word and you were typing, and you noticed that it wasn't actually appearing on the screen. Once it gets around to processing what you've been doing, all of your letters appear in the order that you type them. Letters or characters, I suppose, or any action that you perform on the keyboard. Those key presses are held in a queue, and then the first thing into the queue is the first thing out of the queue. A printer queue, so if you had a single printer which had multiple computers connected to it, and the first thing that gets sent to the printer is the first thing that comes out. You can set those up to have higher priority as well. So you can have a higher priority job jump in front of a lower priority job. CPU scheduling. So this links up to the fetch execute cycle and interrupts. We've got lots of processes executing on a computer, lots of tasks that need the CPU's attention. The scheduling algorithm needs to make sure that all of those get processed, and also there needs to be some sort of order to it, and the best order is the first one there, the first one out, first in, first out, like the queue system. But as well as the queue system, there is a priority to these things. You pressing a key on the keyboard is a pretty low priority compared with a hardware failure or a power failure. Those things come before you pressing a key on the keyboard. Disk scheduling, very similar to the CPU scheduling. You've got input-output requests arriving at the disk, the hard disk, the SSD, the flash drive, whatever it might be, the CD drive, etc. Usually you've got things coming in quickly, and the CPU is sending things quite quickly to the slower devices, and it needs to decide who's having access to the disk and what order am I going to get serviced. Well, it's going to be a queue-based system again. Asynchronous data transmission. So again, the spec link to networking, and in networking we've got asynchronous data transmission, and we've got bits sent one at a time, and they need to be queued up before they're read and understood as to what needs to be done. Used in other algorithms, i.e. pathfinding and Dijkstra's shortest path. So a pathfinding algorithm that uses queues. So other algorithms, there's uses for queues. You can use a queue to reverse a stack. You can use a stack to reverse a queue. There's lots of other ways we can use data structures. And this is just a small list of the available things. And we mentioned quite a few there of requests, or where something needs to be handled or not handled, or handled or put into a queue until something becomes free for us to be able to process it, and that's going to be using a queue. Any system where we've got multiple requests or jobs coming in, multiple clients, and we've got different ways of handling it, one or more handlers. We're going to store those things in a queue, and the first one in and the first one out, with the exception of any priority items. So here we've got a simple past paper question on queues. Deck of cards implemented as a circular queue. So if you're going through questions, highlighting the important bits. So this is a circular queue in a fixed size array. So we mentioned that being called static data structure earlier. And it's named deck queue. So I can identify it there. There it is. And it has indices running from 1 to 52. So in this question, they've not got a 0-based index. It's going from 1 to 52. So that's something to remember. And then it shows the contents of the array itself and the associated pointers. So it's got the pointer, front pointer, rear pointer, and queue size. So the first part of this question, 12 cards are dealt from the top of the deck. What are the values stored in the front pointer and rear pointer and queue size? So this being a queue, we're going to remove from the front. The front is at position 1 and we're going to be removing 12. So our front pointer will then be on 13. Our rear pointer will not change. When we're adding to a queue, removing from a queue, we remove from the front. We don't do anything with the rear. Now what's happened to queue size? Well, queue size will have gone down by 12. The queue size will be 40. Now I previously said that you could take the rear pointer and subtract the front pointer to find out the size. Now in this case, that wouldn't give you 40, it would give you 39. But that's because in this implementation, instead of what we were doing before, where the rear pointer pointed to an empty space, the rear pointer in this implementation points to the last item in the list. So it's just a slightly different way of doing it. So in which case it includes that last pointer, 40, or alternatively, we knew the queue size was 52 anyway. If we subtract 12, which we're dealing 12 cards off, it's going to become 40. The second part of it is an extension of what we've done already, so we'll be taking our answers from part 1 into part 2. Next, the player gives up 3 cards and these are returned to the deck. What are the values now stored in front pointer, rear pointer and queue size? So we've taken 12 cards, now we're returning 3. So adding to the queue, we're not going to be changing the front at all. Adding to the queue changes the rear. And because this is a circular queue, it's going to go around back to position 1. So go from 52, which is the 8 of clubs, and then we're going to be adding 3 cards. So it's going to be adding to position index 1, index 2, and index 3. So the rear pointer would now be 3, adding those 3 extra cards. It's wrapped around with that circular queue style. And we had queue size of 40, now the queue size is going to be 43. There we can see in action the circular queue. Right, time to build our own queue. And we've got a little class diagram here. At the top we've got the name of the class. Then we've got the first section of properties or attributes, and then methods or behaviors. So in this one we've got a pointer to the front, a pointer to the rear, and they're both integers, and the queue contents. And just for this example, we're going to be storing an array of characters. Notice all of the properties I've got a minus next to them. That's indicating that they are private. So the private access modifier, so they can't be accessed from outside the class. The pluses down here, these are public and can be accessed from inside the class, and these two here, the minus ones, are private again. In terms of the methods, we've got onQ, so that's where we'll take a letter in. It's void, it's a procedure, it's not going to return anything. DQ is going to remove from the queue, so it's going to return a character. Peek looks at the front of the queue and returns that, so it's going to give a character back. And we can have size as well, and size is going to give us an integer back. How big is this queue? So we're going to move on to Visual Studio now and try and build this. So we're creating a console application called QDemo. And we get our main appearing. And we're going to go to the Solution Explorer and right click and add a new class. So we could go through new item, but there's also a shortcut here to just go through new class. And we're going to call that class myQ. And just as we said a moment ago, we've got the attributes, which we're going to make private. We don't have to write private, it will be private by default, but we're going to explicitly say it. Private front pointer PTR, and I'm going to declare them both on the same line. Rear pointer PTR, and assign them, because to begin with, when the queue's empty, they're both going to be the same. We mentioned it before that both the pointers at the same location is going to indicate to us that the queue is empty. So there we have front pointer and rear pointer pointing to index 0. We now know it's going to be an empty queue. And the queue contents, we're going to have again, we're going to put the access modifier private char array, so it's a character array, and we're going to call it queue contents. So there we have the properties. Next up, we'll build the constructor. And the constructor is the public method of the same name as the class, so myQ. And when we create a queue, because we're using arrays here, we're going to indicate what size our queue is going to be as well. We're going to pass in a size. And our queue contents array is going to be a new character array of that particular size that we pass through. It sets an absolute maximum size. We said before that it makes the array is a static data structure, so when we declare it with a particular size, for the rest of the running of this object, it will be of this particular size. So if we pass through myQ in size 8, we'd make a char array of size 8, and that's what it would remain. Even if we didn't have 8 objects in there, it would still remain as 8. 8 in size. And then we've got our methods. So we had onQ, so public access modifier, so make sure that we can access it from outside the class. Void, because it's going to be a procedure, and onQ is the name that we're going to give to it. We're going to pass in a character, because when we want to queue our character up, well, we're doing it into a character array, so we better send through a character. I'm just going to pass it in as C. public void on queue. We've got a skeleton there, we'll move on. Next one, public, and it's dequeue. And dequeue is going to return to us a character. So it's not void this time. We've got the public access modifier, and there's no parameters coming in. We don't need any parameters. When we're removing from a queue, we're just removing from a queue. And for now, we're just going to have it return a blank character, just so it doesn't show up any errors. Again, it's not there yet. Peek. So we said we'd have a peek method. Again, public, and we're going to be returning whatever's at the front, and this is the front of a character array. So when we peek, we're going to have a look at the front. So we don't need any parameters, and for now we're just going to have it return a blank space. We also mentioned that we're going to have size because we wanted to be able to see the size of our queue. We know the size of the array is going to be whatever we pass in when we construct the queue, but the size in terms of how many items we have in it, that's what we're interested in. So call it size. Sorry, we need to return something. It's going to be an integer that we return because it's going to be a numeric value. Return int size, no parameters because we don't need to send anything in for that, and we're going to return for now just a placeholder. We'll return 0. We're just trying to get all the methods outlined, and then we'll go and make them fully. Next up we had private methods, so we don't want these accessible from outside. It wouldn't cause too much problems if they were, but we were demonstrating our private access modifiers and our public ones. Is empty, and it's a boolean that we're going to return. If it's empty, return true. If it's not, return false. Just for now, just so we make all of our methods. We've got one more to make. I'm just going to put return true for now. We'll come back to it in a second. And private bool again for is full. And just a placeholder, the return true. Right, so now we're going to go about making or filling in the methods and making them work. So we'll start from the bottom here. We'll start from is full, and I want you to think and consider, given this information, we've got a front pointer, rear pointer, and a char array for the contents of our queue. What will make this full? Okay, give it a pause, give it a think, and then if you play the video on, then you should see what I believe we would be able to indicate if it's full. Okay, is full then. For me, it's going to be when the rear pointer is 1 less than the size of the array. So I can just replace this true with rear pointer -1 equals the queue contents dot size. Earlier on in the video, we queue contents dot length. Sorry, apologies. Dot length for the array. So if the length was 8, the rear pointer, when it's full, I don't know why I did -1 now, thinking about it. If the rear pointer was equal to the queue length, it is full. Because if the queue content, the array was 8, the highest rear pointer position would be, or the highest index would be 7. And so when we've got up to 8, well, it's full. We can't add anything extra. Okay, same thing for is empty. If you pause the video and give yourself a moment to have a go at it. Okay, now this should be the easiest one because I've mentioned it a few times. We're going to have when the front pointer and the rear pointer are the same, that's when it's empty. So we start off our queue with the front and rear as 0 and 0. When they're at 0 and 0, the queue is empty. So we're going to do is empty as being true. Okay, so we've got our error checking area here is empty, so we can check for is full is empty. Size next of all. Again, just using this information, these properties, we should be able to tell the size of the queue. Now this isn't the size of the array because we might not have an array full of data. So it's how much data we've got in this array, how much data we've got in the queue. And the way that we're going to be navigating it, well, I'm going to let you have a go at it first. So pause the video now and then come back to it. Okay, this was one of the things that I mentioned before. We've got front pointer and rear pointer. To figure out the size of this, it's going to be the rear pointer minus the front pointer. For example, if we were to add something to this queue, the rear pointer would have to increment, and then our front pointer would be at 0, our rear pointer would be at 1. 1 minus 0 is 1. If I was to add something else to it, the rear pointer would change to 2. So now I've got 0 minus 2. There's 2 things in our array. If I was to remove something from it, the front pointer would move to 1, and that would still be at 2. And then we've gone down to 2 minus 1. We're just back to 1 thing in our queue. So our rear pointer minus our front pointer will help us work out the size of our queue. Not the size of our array, that's dot length, the queue contents dot length, but the size of our queue. Next up, peak. Again, pause the video, give yourself a moment to try and work it out yourself. Okay, with peak, first thing to check is the queue actually empty? Because we can't peak at nothing. We don't want to have any sort of underflow. So I have an if statement. If is empty, then sorry, let's go if. Yeah, we'll go if is empty. Underflow. Error. Empty queue. And we can get it to return just a blank character. Anything else, we want it to return what is at the front. So how do we access the front? Well, we've got the array there, and we know what the front is because we've got a front pointer pointing to it. So that will return the contents pointed to by the front pointer. Okay. With peak done then, give DQ a go. Pause the video here and have a go at it. Okay. With DQ, again, we're checking whether there's an underflow occurred, because yeah, we don't want to try and remove something from an empty queue. So we output the error message here and then return just a blank. Anything else, we want to return the contents of the front pointer. However, this is DQ as well. This is DQ. So we also want to have the front pointer move up, because the front pointer needs to increment. So if we increment the front pointer, we're not pointing to the one we wanted to look at. So if we just do -1 there, then we're incrementing the front pointer ready for next time, and subtracting 1, we're seeing where the pointer was previously looking. We could do it in a number of different ways. In fact, I will, just to show you. We could make a temporary char and have the queue contents, the front pointer point at the contents at the position the front pointer is pointing to stored in temp, and then incrementing the front pointer before returning what temp is. So we're taking a copy of whatever's at that position in the array, we're incrementing the front pointer because we've DQ'd that one now, so we're on to the next, and then we're returning what we took a copy of. So we're DQing there. And finally, one more method for us to try, onQ. So again, pause the video and give it a go. Okay, onQ. Again, we first need to check that the queue isn't already full. So if it's full, output an error message. Overflow error, queue is full. And it will do nothing else. If the queue is full, just output that and then move on. If the queue is not full, however, else, queue is not full, then we want the character C to be put onto the queue. And where do we enter a queue? Well, we enter it at the rear pointer. The rear pointer is pointing to the next empty space in the queue. So we're putting C into that position. But not only that, the rear pointer needs to then increment, because the rear pointer needs to be ready for the next position on the way. Okay, so that's then all the methods created. We can go into the program and the main, and we can try these out. So we called our queue myQueue. So there it is. Just going to name it queue and equal to new myQueue. So this is us calling the constructor. You see we've got our variable in there, size. So we'll, like in the examples we used earlier, we'll do 8. And then we can see what we can do with queue. Well, the public methods are DQ, onQ, peak, and size. So we're going to do a number of things here. We're going to test it out. So first of all, we're going to look at what the size is. So we're going to concatenate the word size with a colon and just call queue.size. Okay, so that should return to us 0, because the queue should be empty. Console right line, sorry, not right line yet. Then we want to have a go at entering something into our queue. So queue.onQ. In fact, we should just test whether we can dequeue from an empty list first of all. So dequeue 1. So I'm going to number these so I know when they were called. So size 1, dequeue 1. So dequeue should return to us a character, but we're anticipating that it should also output an error message here because we tried to dequeue from an empty list. Underflow. So error underflow. Then we'll try and queue it up on queue, and we'll give it the character A. We'll assume it works, so we'll also on queue B. And then on queue C. And then we'll do quite a few more all in one go. So that's 3 done. I'll select 1, 2, 3, 4, 5 rows. Don't want 5 rows, sorry. Yeah, 5 rows. 1, 2, 3, 4, 5. And if you're selecting them whilst holding Alt, you'll get 5 cursors appearing, or however many lines of code you do. It's just a little shortcut where you can type more than one line at once. When you're doing this, however, you don't get the IntelliSense automatic things popping up for you, which is a disadvantage. But you get to type across multiple lines. And then we want to do D, E, F, G, and H. How many is that? 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 there. So we anticipate that they're all going to work fine and not give any errors. And then we're just going to do one more on queue to try and overfill this queue. On queue I. So we're expecting an error overflow here. Because we set out with our queue of size 8, and if we're trying to put 9 things in, 1, 2, 3, 4, 5, 6, 7, 8, 9 things in, it should give us an error. We expect an error there, and then we'll test whether dequeue works. So we've done dequeue 1. So dequeue 2, we call dequeue and it should return to us a character. It should return A, because that was the first thing in. So this should output dequeue2 and the character A. If we carry on and call this a few times, changing what number gets output there. So we should be outputting A, B, C, D. Well, because A, B, C, and D were put in that order. This is a structure that is a first in, first out structure. So we can continue to keep dequeuing. DQ5, DQ6, DQ7, DQ8, DQ9, and it would output A, B, C, D, E, F, G, H, and just for, although we will have tested it already, just for thoroughness, DQ10, we should get a error underflow like we had at the start, because by this point our front and our rear pointers should be in the same position. They should be in position 8, which doesn't exist in the array that we're going to make. But yeah, we know that if we try and DQ and it finds out that the front and rear pointers are at the same location, the queue is actually going to be empty. So that's hopefully what we'll see, and we'll put a console read line in, and that will stop the program and allow us to see what's going on. So we'll give this a run, let it compile, and away it goes. So, I didn't check size again. I'll have to check size again in a moment. But certainly starts off working exactly as we anticipated. The size is 0. When we tried to DQ from an empty queue, we got an underflow error message. Fantastic. Yeah, indeed, it was error message with DQ1. We then put in 9 things, and we got 1 overflow message with the queue being full. We then DQ2, and it output in the same order that it went in, first in, first out, and we tried to take out as well when the queue was empty, or when the front pointer and rear pointer were at the same position, so it was not able to do that. So things to add to this, to finish off the testing, is to check the size. So we can call size again. In fact, we could do it after every single on queue. So size 2, we expect it to be 1. Now we won't do it after every single one. Size call number 3, we'd expect it to be 3. And then size call 4 here, so we've entered 1, 2, 3, 4, 5, 6, 7 letters to our queue. We'd expect that to be 7. And just for thoroughness, the 5th call, we'd expect it to be size 8. And even though we tried to on queue again, we'd expect another call to size there to still be 8, because we shouldn't have added anything. And then when we're DQing, we could check some more sizes. So size 7, we'd expect to be 7 now, because we've DQ'd A. We would expect it to be after F, size call number 8. Let's think about what we've done here. So we DQ'd A, so 1, 2, 3, 4, 5, 6. So we'd expect the queue to still have 2 things in it, just the G and the H, so we'd expect it to have output 2. And another thing we didn't test, I will test it out now. We'll peak as well. We test our peak. So peak 1. And it doesn't really matter if we've tested it this far down. Q dot peak. So we'd anticipate that this should output G, because G would be the thing at this point in the list, and then when it DQs it should still output G because peak shouldn't have removed it. And then we can do the peak 2 just before H. Peak 2, we'd expect H to be at the front, and then if we do peak 3 when we've removed the H from the queue as well, we'd expect it to output error underflow. So peak 3. So quite a few tests, but all kind of an all-in-one test. I could have slowed it down and tested the things individually, but we've tried to test everything in one go here. Let's give it a go. Let's check our understanding. So we had size 0, we had an underflow error as we anticipated. We then were on queuing and we got the size to be 1. Yes, we anticipated that. The next size call was 3, we got that as well. The next size call was 7, yes. The next size call was 8, so it's clearly working. When we tried to put another thing in, the size remained 8, so it's matching very well here. Then we output A, yes it did, the size went down to 7. We output B, C, D, E and F, and the size went down to 2, we anticipated that. G, and then we peaked G, so the peak works as well. Then we DQ'd G, we peak H, then we DQ'd H. We got an underflow when we tried to peak when the queue was empty, and we got an underflow when we tried to DQ when the queue was empty. Excellent. So our basic queue works fine. It does have that issue of, with it being a linear queue and is using an array, it will run out of memory because we just keep incrementing the rear pointers, and that's where the circular queues come in. So in the next video we'll cover creating the circular queue and seeing how that improves this. So right now our queue wouldn't be able to add any more things to it. We could also have a look at doing the queue with a dynamic data structure as well, and we could also have a look at the queue and moving the contents up, so having the front pointer always be at 0 and just shifting all of the elements up every single time.